I'm Anuradha Mathur. I teach physics at Modern School Vasant Vihar in New Delhi. In this unit on work power energy in our previous lessons, we have learned the meaning of the word work. We have learned how to calculate work using graphs and equations. We have understood the meaning of power. We have gone ahead and learned the meaning of energy as ability to do work, concept of mechanical energy as in kinetic energy and potential energy. We've done conservation of energy, work energy theorem and its applications. Today we are going to learn about potential energy stored in springs. You have seen springs in daily life. Some of the common examples are the springs inside small ballpoint pens, in watches or toys where there is a leaf spring and you wind the toy and allow it to run, or simply a shape like this which stores energy. When I pull it and leave it, it goes back. This spring action is because of the shape that we have given to this wire. After all, the wire doesn't do this kind of storing of energy as the spring does. So, we need to study the spring in general and understand why it behaves so when its shape changes. As an example, let us consider a spring to which is attached a small weight, a scale which shows the extension or the length of this spring. I have a 50-gram weight and I am going to load it here, and we are going to see what change will take place in this spring here. As I load, you will note the reading. I will note it for you. So, load and the extension. So, the load I have here is 50 grams and the reading, if you can read well, is 2. I can take another weight, make the total weight stretching the spring to 100, and this 100 is giving me a value of 3 as read off from the scale attached to the spring. Adding more weights, as you can guess rightly, is going to extend it. What you must also see here is that as we extend the spring using equal weights, is the extension remaining constant? This for 200 would become 5, and I have one more weight here which will make it 250. So, for 250, as you can see, the extension is 6 centimeters. Noting this down, we can plot a graph for this, and let me show you what this graph will look like. For the moment, I will remove this. These are our measurements. We loaded the spring and these are our extension values as recorded from the scale attached to the spring. If we were to plot a graph of load and extension, what do you think it will look like? So, let us put load on the x axis and extension on the y, and if you plot this, say 50, 100, 150, 200, 250 and corresponding extensions of 2, 3, 4, 5, 6 like that, you will get a straight line. It is not difficult to imagine why this straight line is coming. It is the winding of the spring which is so uniform that it allows the extension to be uniformly placed for each of these threads. Now, this property is not available for the wire that makes up the spring. Let us study why and understand how springs store energy and are able to do work because of their shape. Let us understand why the spring behaves in this peculiar manner. As an example, let us again take our apparatus back and see what is happening at this moment. The weight is pulling this spring, and because the extension allows it to stay right here, it is not going down further because of the weight. That means there must be some force which is generated inside the spring. Notice, if I were to remove any one of these, the spring is shrinking back. That means there must be a certain force which is developing inside it, pulling it in the opposite direction against gravity, or the gravitational pull generated by the weights that are hanging here. This means that there is a restoring force which is developed inside this. In every system, whenever we put any force to it, there is a restoring force which develops. In some cases more and in some cases less. Obviously, it depends upon the shape of that particular body. Like in this case, you can take an example or think about plastic balls. If you have a strip of plastic, it does not undergo any kind of changes as a plastic ball would if you were to compress it. So, keeping this in mind, we now have a reason to believe that the restoring force must be responsible for this behavior. Let us now see in cases when a load is stretching a spring, what is the direction of this restoring force and what is the displacement which is being caused in it. And you can imagine either a vertical spring with the load as we had in our example, or we could even imagine a horizontal spring of which one end is attached to a fixed point and the other one has a weight which can move or can be moved. I will draw that for you and we can see. I am going to draw for you a horizontal spring system, and let us say I have a base which is frictionless and a spring attached here and a mass or a block, you can imagine anything like this, which is attached here. This is in its rest position. If I were to stretch it slightly, that means my spring now would be opened out a little more and say my block rests in this position. That means it is stretched by a distance x. Where is the restoring force that is going to develop in it? You can imagine if I were to stretch it like this and leave it, the restoring force would be in the opposite direction like it was in the case of the vertical spring as I showed you. So, in order to talk about it, if the displacement is in this direction, a restoring force develops in the opposite. Likewise, if I were to leave it, you can imagine a situation where the block would be somewhere in this location and the spring compressed by the same extent as x. Now, this time the displacement is in the opposite direction and our force, restoring force, would act again towards this mean position that we have for the spring where there was no load. So, this is my 0 position, this is my displacement in the positive direction and this is my displacement in the negative direction, and in every case the restoring force is opposite to the displacement. Our example earlier had said that the force which would be generated would be equal to the deforming force. Why? Because at one point the deforming force was in one direction, the restoring force must be supporting it as there was no movement in the vertical direction. So, this is proportional to x, and from here we can also see that it would be equal to minus some k times x. The minus sign is important to understand over here. The relevance of minus sign here is that this displacement vector is opposite to the force vector. So, because they are in different directions as I just showed you with the arrows, this negative sign becomes very, very important. the magnitude of restoring force remains equal to kx, but because the direction has to be accounted for, you put this minus sign in order to make this equation a little more usable. Now, this quantity k is called the spring constant. The spring constant will depend upon how the spring is wound. That means different springs are going to have different spring constants. I have got two springs over here, and I am going to suspend equal weights from it, and we are going to see, because of their spring constant, is there any difference in their extensions. Notice there is one spring here and the other on the other side, and I have equal 50 gram weights which I am suspending from one from this one. It has been stretched a little, and let us see how much of stress is produced in the other one. Please see, this one stretches so much more. What can you predict about its spring constant? Which one is going to have a higher spring constant and which is going to have a smaller spring constant? I will leave that for you to decide, and then understand why different types of springs are used in daily life. Motorcycles have springs, swing doors have springs. Springs are there in so many spots and so many places. Now, we are going to understand and find out how much energy does the spring store in it. So, we are watching and seeing that in a spring a deforming force is causing deformity, whether it is compressing it or stretching it, and a restoring force is coming up inside it, and that is going to bring it back to its original shape. So, how much of energy is involved, because the ability to do this work of change is being done by the restoring force. So, if we were to plot the graph between restoring force and the external displacement, what do you think it will look like, and what will be the values in it? Say this is my y axis and my x axis, and I place over here x, which is positive x, and this is negative x. Please continue to think about the earlier example of the horizontal springs. And if you were to talk about the force extension curve, it will look like this. Why? Because the force, restoring force, was negative when this was positive, and it was positive when the displacement was negative. So, this is the kind of graph you will get, and say I am talking about only a maximum displacement of x m. In that case, my value for the force, this one here, this value becomes F equal to minus k x m. Now, what is the value for force here? Before, for this extension, 0, and what is the value here? K x m. So, the average value of force becomes 0 plus k x m divided by 2. And how much of work would be associated with it? Force into the displacement from our previous knowledge, and this would give us k x m by 2 multiplied by x m. This value is half k x m square. This is the energy that is stored in the spring, and this is the energy that causes it to do work. That means, change its configuration back to its original one. Now, springs therefore have great attraction in daily life, because all you have to do is to compress them or change their shape, and they store up this energy, and they can do the job for you whenever you want. One such application is in automobile engineering. When making a car, what they do is to find out what would happen to it in case of an untoward accident. So, they simulate this using springs. Let us do an example of that, and let us calculate for ourselves how much help it does for making safe cars and good cars for daily life. Let us consider a car, and let us say this car is moving in this direction, and let us say it is moving with a speed of 18 kilometers per hour, and say its weight is 1000 kg. It is a small car. So, this car is under test and it is moved towards board which is attached to springs, and what we are expecting is that when it strikes here, nothing should happen to the car and nothing should happen to the board. We are moving at a fairly slow speed of 18 kilometers per hour. The spring constant here for this spring is equal to 6.25 into 10 raised power of 3 Newton per meter. I hope you can figure out how you get this unit Newton per meter from F equal to kx. K will be F upon x. So, force Newton per meter, that is its unit. And let us see from this simulation what it becomes. Now, what is the energy that will be stored in this spring once this strikes it? So, the kinetic energy of the car is to be calculated, which would be given by half mv square, and to find out the v value in meters per second, we must remember that 36 kilometers per hour is equivalent to 10 meters per second. So, 18 kilometers per hour is going to work out to 5 meters per second. So, our kinetic energy is 1000 multiplied by 5 into 5 for meters per second, and this value comes out to be so many joules. And then what will be the energy stored in this spring? That will be equal to half k x square. We can find out how much will be the compression in this spring and how much of that should be taken up by the fenders which are attached here. So, we equate 12.5 into 10 raised power of 3 equal to half, and put the value for k as 6.25 into 10 raised power of 3 and involve our x square. From here x value comes out to be 2 meters. That means, this will compress 2 meters on an impact by a car of 1000 kgs moving with a speed of 18 kilometers per hour, and you can make the choice of material for this region so that nothing happens to the car. Now, this is done by all car companies, and that is why it is a very, very important way of creating safe modes of transport, safe cars on the road. We do not want anything untoward happening. In the example with the car, we ignored a lot of things like the friction by the road and the time of impact, etc. So, obviously, our answer is going to be very different from real life. In any case, it gives us a method of finding out how to deal with it. I am going to show you one more experiment in which a spring can be used to find the weight of things. How do we do that? You can determine a relation between periodic time of a spring, because there is a restoring force in it, it is ready to oscillate. So, you can use the method of dimensions and find a relation between time period of a spring constant and the mass that may be hanging from it. And this relation comes out to be, and if I were to use this as an example here, and I can find the periodic time for this oscillation for 20 oscillations. I know the weight that is hanging here. I can put an additional weight on this and determine its value for time period. The new value of time period and the earlier value can be placed in such a way that I can determine mass of any object. This goes without saying that the value of k would be found from our load extension graph as we had plotted it earlier, and that value would be 1 upon the slope of the line. You could figure that out on your own and see how the load extension graph gives you the value of k, the value of m plus the additional mass will give us a new value for t. So, comparing it to the earlier value with a certain load, I can determine this value m dash. In this lesson today, you have learnt the value of springs, you have learned to appreciate how the springs store energy, how they contribute in our daily life, because changing their shape makes them store energy, which is potential energy, and therefore gives them the ability to do work. Thank you.